or several thousand years. Mathematicians believe that the fourth dimension cannot exist because we cannot picture it in our minds. 2,000 years ago, Euclid, one of the greatest mathematicians ever lived, said that a point has no dimension at all. A line has one dimension, length. A plane has two dimensions, length and breadth. A solid has three dimensions, length, breadth, and height, and there it stops. Nothing has four dimensions. These sentiments were echoed by the philosopher Aristotle, who apparently was the first person to state categorically that the fourth spatial dimension is impossible. In On Heaven, he wrote, "The line has a magnitude in one way, the plane in two ways, and the solid in three ways. And beyond these, there is no other magnitude because the three are all." Furthermore, 500 years after Aristotle's death, the astronomer Ptolemy from Alexandria went beyond Aristotle and offered, in his book On Distance, the first ingenious proof that the fourth dimension is impossible. First, he said, draw three mutually perpendicular lines. Then, he argued, try to draw a fourth line that is perpendicular to the other three lines. He reasoned that no matter how one tries, four mutually perpendicular lines are impossible to draw. So, he claimed that a fourth perpendicular line is entirely without measure and without definition. Thus, the fourth dimension is impossible. What Ptolemy actually proved was that it is impossible to visualize the fourth dimension with our three-dimensional brains. So, none of the mathematicians could develop the idea of the fourth dimension. One of the main reasons is that scholars have wrestled with the theorems of Euclid's geometry. The usual axioms of Euclid were, the shortest distance between 2 points is a straight line, two parallel lines never meet, and the sum of the interior angles of a triangle adds up to 180 degrees. But this is only true if one stays within the confines of flat surfaces. Now, if one strays into the world of curved surfaces, it is incorrect. On spherical surface, two parallel lines meet at a point, and the sum of angle of a triangle is greater than 180 degrees. In fact, the mathematicians of Europe began to realize that even Euclid's Elements, which had been revered for 2,000 years, was incomplete. The time was ripe for a revolution, but who would lead it, and what would replace the old geometry? Finally, the decisive break with Euclidean geometry came when Carl Friedrich Gauss, one of the greatest mathematicians ever lived, asked his student Bernhard Riemann to prepare an oral presentation on the foundation of geometry. Bernhard Riemann was born in 1826 in Hanover, Germany. He was the son of a poor Lutheran pastor, the second of 6 children. Beset by the daily struggle to put food on the table, Riemann's father might have sent the boy to do menial labor. Instead, he scraped together enough funds to send his 19-year-old son to the renowned University of Göttingen, where he first met Carl Friedrich Gauss, the acclaimed prince of mathematicians. Gauss was keenly interested in seeing if his students could develop an alternative to Euclidean geometry. Riemann, however, was terrified. This timid man, terrified of public speaking, was being asked by his mentor to prepare a lecture before the entire faculty on the most difficult mathematical problem of the century. Over the next several months, Riemann began developing the theory of higher dimensions, straining his health to the point of a nervous breakdown. His stamina further deteriorated because of his dismal financial situation. He was forced to take low-paying tutoring jobs to provide for his family. Furthermore, he was becoming sidetracked trying to explain the problems of physics. In particular, he was helping another professor, Wilhelm Weber, conduct experiments in a fascinating new field of research, electricity. Electricity, a phenomenon known to the ancients in the form of lightning and sparks, took on a new significance in the early 19th century. It became the epicenter of physics research, with the revelation that a current of wire passing across a compass needle could set it spinning. Similarly, the movement of a bar magnet across a wire could induce an electric current, a principle now known as Faraday's law. Riemann, deeply moved by these revelations, saw in them a profound connection between electricity and magnetism. Filled with a sense of exhilaration, he threw himself into Weber's laboratory, firmly believing that the new mathematics he was formulating would unlock a comprehensive understanding of these forces. After several months of deep focus, Riemann finally developed a startling new picture of the meaning of these forces and their connection with the fourth dimension. Since Newton, scientists have considered a force to be an instantaneous interaction between two distant bodies. Physicists called it action at a distance, which meant that a body could influence the motions of distant bodies instantaneously. Newtonian mechanics undoubtedly could describe the motions of the planets. However, over the centuries, critics argued that action at a distance was unnatural because it meant that one body could change the direction of another without even touching it. In response, Riemann developed a radically new physical picture. To illustrate his ideas, Riemann apparently borrowed from Gauss's analogy of a two-dimensional bookworm living on a two-dimensional piece of paper. Grab a piece of paper and put a two-dimensional worm in each opposite corner. Now, draw a straight line connecting them. Imagine one worm traveling along this line to visit the other. Along the way, the worm might feel various forces, like gravity, acting on its tiny body. These forces are invisible, though, so the worm can't see them. All it perceives is its universe, which is this flat sheet of paper. Now, crumple the sheet of paper into a ball. Because of the paper's geometry, worm bodies and the mysterious forces would also be crumpled. However, these 2D worms wouldn't notice this distortion, which was happening inside the third dimension. They would still believe that the world is flat and assume the shortest distance to one of its friends is the straight line drawn earlier. But for someone who has access to the third dimension, it's clear that the worm is not traveling in a straight line and can see shortcuts, like digging holes through the paper. This example made Riemann realize that the force isn't a mysterious action at a distance, but rather a result of the unseen warping caused by the third dimension. Thus, Riemann made the first momentous break with Newton in 200 years, banishing the action at a distance principle. To Riemann, force was a consequence of geometry. Riemann then replaced the two-dimensional sheet with our three-dimensional world crumpled in the fourth dimension. Like little worm, it would not be obvious to us that our universe was warped. Riemann concluded that electricity, magnetism, and gravity are caused by the crumpling of our three-dimensional universe in the unseen fourth dimension. Thus, a force has no independent life of its own. It is only the apparent effect caused by the distortion of geometry. By introducing the fourth spatial dimension, Riemann accidentally stumbled on what would become one of the dominant themes in modern theoretical physics, that the laws of nature appear simple when expressed in higher dimensional space. He then set about developing a mathematical language in which this idea could be expressed. Finally, he delivered his oral presentation in 1854. In retrospect, this was, without question, one of the most important public lectures in the history of mathematics. Word spread quickly throughout Europe that Riemann had decisively broken out of the confines of Euclidean geometry that had ruled mathematics for 2 millennia. News of the lecture soon spread throughout all the centers of learning in Europe, and his contributions to mathematics were being hailed throughout the academic world. His talk was translated into several languages and created quite a sensation in mathematics. Now, let's delve deeper into Riemann's paper. So, what was written on it? Like many of the greatest works in physics and mathematics, the essential kernel underlying Riemann's great paper is simple to understand. Riemann began with the famous Pythagorean theorem, one of the Greeks' greatest discoveries in mathematics. The theorem establishes the relationship between the lengths of the 3 sides of a right triangle. It states that the sum of the squares of the smaller sides equals the square of the longest side. For 3-dimensional space, the theorem can easily be generalized. It states that the sum of the squares of 3 adjacent sides of a cube is equal to the square of the diagonal. So if A, B, and C represent the sides of a cube and D is its diagonal length, then it is now simple to generalize this to the case of n dimensions. Imagine an n-dimensional cube. If A, B, C, and so on are the lengths of the sides of a hypercube and Z is the length of the diagonal, then, remarkably, Even though our brains cannot visualize an n-dimensional cube, it is easy to write down the formula for its sides. But mathematically, manipulating n-dimensional space is no more difficult than manipulating three-dimensional space. It is nothing short of amazing that on a plain sheet of paper you can mathematically describe the properties of higher dimensional objects that cannot be visualized by our brains. Riemann then generalized these equations for spaces of arbitrary dimension. These spaces can be either flat or curved. If flat, then the usual axioms of Euclid apply. But Riemann also found that surfaces can have positive curvature, as in the surface of a sphere, where parallel lines always meet and where the sum of the angles of a triangle can exceed 180 degrees. Surfaces can also have negative curvature, as in a saddle-shaped or a trumpet-shaped surface. On these surfaces, the sum of the interior angles of a triangle add to less than 180 degrees. Riemann's aim was to introduce a new object in mathematics that would enable him to describe all surfaces, no matter how complicated. This inevitably led him to Faraday's concept of the field, which was recently developed. Simply put, a field is a collection of numbers defined at every point in space that completely describes a force at that point. For example, 3 numbers at each point in space can describe the intensity and direction of the magnetic lines of force. Another 3 numbers everywhere in space can describe the electric field. Riemann's idea was to introduce a collection of numbers at every point in space that would describe how much it was bent or curved. Just as the derivative of a curve captures the slope of the tangent line at each point along the curve, which helps us to identify how the curve bends, Riemann discovered that in 4 spatial dimensions, one requires a set of 10 numbers at each point to describe its properties. Regardless of how crumpled or distorted the space might be, this set of 10 numbers at each point adequately encodes all the information about that space. Today, this set of numbers is referred to as the Riemann metric tensor. Roughly speaking, the greater the value of the metric tensor, the greater the crumpling of the sheet. No matter how crumpled the sheet of paper, the metric tensor gives us a simple means of measuring its curvature at any point. If we flattened the crumpled sheet completely, then we would retrieve the formula of Pythagoras. This metric tensor allowed him to erect a powerful apparatus for describing spaces of any dimension with arbitrary curvature. Previously, it was thought that terrible contradictions would arise when investigating the forbidden world of higher dimensions. To his surprise, Riemann found none. In fact, it was almost trivial to extend his work to n-dimensional space. Riemann persisted with his work in physics. In 1858, he even announced that he had finally succeeded in a unified description of light and electricity. He wrote, "I am fully convinced that my theory is the correct one, and that in a few years, it will be recognized as such." Although his metric tensor gave him a powerful way to describe any curved space in any dimension, he did not know the precise equations that the metric tensor obeyed. That is, he did not know what made the sheet crumple. Unfortunately, Riemann's efforts to solve this problem were continually thwarted by grinding poverty. His successes did not translate into money. He suffered another nervous breakdown in 1857. After many years, he was finally appointed to Gauss's coveted position at Göttingen, but it was too late. A life of poverty had broken his health, and like many of the greatest mathematicians throughout history, he died prematurely of consumption at the age of 39, before he could complete his geometric theory of gravity and electricity and magnetism. These crucial developments would be left to Maxwell and Albert Einstein,